Dear students, so welcome to the next lecture of wireless communication. So in the last lecture we started discussing about communication networks, and in this lecture we will continue that topic, but under that topic we will start with network topologies today. So so let's see what we have. So usually when we talk about topology, the term topology basically means it's the geometric arrangement of the network's nodes. Okay, so so in the last class, in the last lecture, you saw there was a topology uh, like this. So we had some switching nodes, and they were connected like this, and then there were some end systems attached to these switching nodes. Let's say your computer or PC, or it can be your mobile phone. So so this basically this arrangement of the nodes and the links, uh, this is actually called a topology. It's the geometric arrangement of the network's nodes. So common topologies include star, ring, and bus. There is also a topology called mesh. Okay, so we will discuss about star, ring, and bus now. But mesh is a topology which is little more connected. So let's say what you have in this picture is a star network. Let's say a star topology which looks like a star. Okay, you can have a ring topology. So this actually is an example of a ring that I just draw. uh, a ring can also look like this. Uh, so these are the nodes and these are the links, but essentially this is also a ring. And then when you have a little more connectivity in the ring, let's say you connect these two nodes or these two nodes. Okay, or in this drawing, let's say these two nodes are connected, these two nodes are connected, then this forms a mesh. So a ring is a special case of a mesh. Okay, a mesh means uh, more connectivity, like as I just drew. So for example, let's say if we have 4 nodes, okay, then if you connect them like this, in the form of a square, then it still is a ring topology. But then you can make it a fully connected mesh. Okay, by connecting from one node to all possible other nodes. So each node here, let's consider this example. Okay, so each node here can connect to 3 other nodes. Okay, so if you have that type of connectivity where each node connects to all the other nodes, then this is a fully connected mesh. Fully connected mesh. Okay, um, you can also have a semi fully connected mesh. Okay, so let's say in this example, again you can just have this. So this is a mesh but not a fully connected mesh, because this node is connected only to these two and not this one. So you can have different variants or different types of geometric arrangements. Okay, so mesh is the more common form of network. Most of the large countrywide networks, they are mesh in structure, and we can have simplified networks like bus, ring, and star also. So we are not discussing mesh in this particular set of slides, but we are only discussing star, ring, and bus. But it's good to know what is a mesh. So, so coming to the star network. So this is the example of the star network, as you can see. So there is a central hub, okay, and most of the other devices are connected to a large host computer or CPU termed as hub. And time sharing is allowed so that several users can share a central processor. So these devices in the star network are sharing this hub, and they are connecting to each other through this hub. So for example, let's say this node and this node will connect through the hub. So and the resources in the hub are utilized in a time shared manner. Okay. Moving on, we have the ring topology. So again, it's very evident from the figure itself that you connect the nodes in a ring form, and messages travel around the ring, and each node reads those messages addressing it, and and the nodes wait for a token before they transmit. Okay. So uh, if you want to know more about what is a token and how these nodes in the ring network, wait for a token before they transmit, I would suggest you to read the textbook that I mentioned by William Stallings. So you will find more details there. Okay. Uh, I leave it to you for reading in the book that you have. Then you have a bus network. So it's a similar to the ring, but then the ends are not connected. So this is the topology of a bus. So if you see these two end nodes are somehow connected, then this will form a ring. Okay, so the difference is that the ends are not connected, and all communications carried on a common cable or a bus and are thus available to each network's node. So this is the common bus, and everyone gets access to this bus. um, there are some issues in bus networks. So you can have contention. So for example, if a line is unused, the device can transmit its message as well. Sorry, if a line is unused, the device can transmit its message at will. But if more terminals are initiating messages simultaneously, they must stop and transmit again at different times. So let's say if these two are trying to send messages to this one simultaneously, then this there will be a contention. Okay. So this bus cannot be used simultaneously by these two. So either this one or this one has to wait and transmit again at a different time. So talking generally about the network architecture. So basically architecture defines the broad outlines of the system. So there can be open versus closed architecture. So in an open architecture, the components and the devices used are off the shelf, and they can be used by anyone, and all of the components, they conform to a common approved standard. Whereas, let's say in a closed architecture, the design of the component is proprietary. So that means um, it makes it difficult to connect the system to other systems. Okay. So let's say um, a switch manufactured by company A, if it is proprietary, then only company A can use that switch. Okay. um, and nobody else, let's say company B, cannot use the switch manufactured by company A. Okay, whereas in open architecture, um, all the components manufactured by A and B are interoperable. Okay, so if you have a network with like this, let's say, and then say this switching nodes uses components of company A, and this switching node uses components of company B, and if it is an open architecture, then this is feasible. Okay, because company A products and company B products, they conform to a common approved standard. However, if company A doesn't conform to the common approved standard and makes its products proprietary to itself, then nobody else can use it. So company A can use its components in its own internal network, let's say. So that's a closed architecture. Uh, then you can have peer-to-peer versus client-server architecture. So in a peer-to-peer case, each network's node has equivalent capabilities and responsibilities, and it's usually simple, cheap, low performance under heavy loads. So one example of a peer-to-peer network is the Bitcoin network. So this is a classic example of a peer-to-peer network where there is no centralized authority that controls the nodes. Each node has equivalent capabilities and responsibilities. So another example of a peer-to-peer system is a file sharing system between a campus LAN, where you upload some files, and then you can also find copies of different files that others have shared and uploaded, and you form a peer-to-peer network to exchange data. And these are usually simple, cheap, low performance under heavy loads. There could be a client server model as well. So each network's node is either a client or a server. So a server is usually a very powerful computer dedicated to management and orchestration. So these servers, they actually manage the different clients, and clients are the less powerful computers on which users run their applications. So these clients rely on the servers for resources, for example, files, devices, processing power, and usually this architecture is a bit of expensive and also complex, and it's high performance under heavy loads. So this is the client server model. Now let's move on to the concept of quality of service. So whenever we are talking about a communication network, we talk about quality of service. So let's say when you are sending some data over a network, um, the data can be of different types. It can be voice, audio, and video traffic. And depending on the types, the requirements uh, can be different. Okay, so there can be requirements of steady delivery. There can be requirements in terms of delay, how much delay you can tolerate, what could be the minimal throughput, etc. So for example, let's say if you have a streaming video going on, such as let's say a live sporting event, then you are basically not looking for something that will stop your video from time to time, and there will be a delay, and there will be buffering of the video. So for this type of service, you need a high quality of service in terms of delay. So so whatever be the service, let's say when you're talking on the phone to your friend, that's a voice service, probably you can afford a little more delay, a little more packet loss, and so and so. So again, the quality of service for a voice traffic uh, is I mean, the requirement for the quality of service for a voice traffic can be lower than the requirement for quality of service for a video traffic. So depending on the types, and the requirements varies, and the quality of service also varies. So for example, in a data traffic, all you need is an eventual error free delivery, okay? Even that, if that means that there are some retransmissions involved, and and that can also, allow you some variation in throughput during the transmission. So and usually you desire a higher throughput, but then some variations can also be acceptable, and eventual error free delivery, as long as that is ensured, you are good. This type of data traffic is, let's say, can be interactive or non-interactive. In case of an interactive data traffic, um, one example of an interactive data traffic is uh, web page interactions, or transactions. Non-interactive is the background downloads of files or email. So so the idea is that, like, how to provision quality of service for your communication network. Like when you are designing a network, this is the main thing that you need to guarantee. So there can be different ways of provisioning the quality of service. So for example, you can do the first approach, which is the over provisioning approach, where you ensure that there are high data rates and low congestion throughout, and all traffic proceeds virtually unimpeded, okay? There is no prioritization, um, and everything is uh, going without any obstacle, okay? So this is only practical in wireless systems that have abundant bandwidth, okay? So if you have lot of bandwidth, then you can do a bit of over provisioning, okay? But this is not always the case. In most systems, your bandwidth is limited, and you have to make some arrangements to still provide a certain level of quality of service even with the limited bandwidth. And in those cases, you can employ these approaches. So prioritization without guarantees and prioritization with guarantees. So in the case of prioritization without guarantees, some packets are marked as high priority. So again, if you go back to the analogy of the postal system, like for registered post and speed posts, okay, you have high priority, okay. And then for other regular posts where the price is also low, you have no prioritization, okay. So this is prioritization. And then without guarantees means that, um, there will be no guaranteed that, or no acknowledgement that the packet is received, okay. So compared to the case where you have guarantees, so here, uh, you have prioritization of the packets, but then the packets are also tracked, and you have some guarantee that the packet is, received. So So these are the two methods of provisioning of QoS. Now we will move on to the concept of protocols. So we when we talk about communication networks, we also talk about communication protocol. So basically, a communication protocol is a system of digital message formats and rules for exchanging those messages. So basically, whenever you are transmitting data over a communication network, there are certain rules you need to follow. Okay, if you don't follow the rules, then um, things will be very haphazard and things will be chaotic. Okay, so everyone is trying to share the common communication network infrastructure, right? So imagine when you are driving on the road and there are like a lot of other vehicles, like there is a bus, there is a car, there is a bicycle, there is a scooter, everything, and then there are pedestrians. So everyone is sharing the streets or the common infrastructure, and then imagine there are no traffic lights, okay, no rules to follow on the road, then there will be a chaos. There could be traffic jam, there could be accidents. So that's why rules are important, and then the rules for exchanging messages over a communication network are basically called protocols. Okay, so usually the communication protocols perform the following functions for efficient and error-free transmission of data. So what are those functions? Data sequencing. Okay, so this means a long message which is to be transmitted is broken into smaller packets of fixed size, and then the packets are numbered, and this process is called data sequencing. Okay, so you saw this in packet switching, like when we were discussing about packet switching. Uh, I repeatedly mentioned this, that the long message was getting divided into smaller packets of fixed size, etc. So this is the uh, first task of a communication protocol, to do data sequencing. Then the next task is data routing. So this is basically to find the most efficient route between the source and the destination before sending the data. So again, you have to find out the path through which your data will travel. Okay, so that part is done by data routing. The next task is flow control. So again, when you studied packet switching, you saw that packet switching allows different data rates at the transmitter and the receiver. Okay, even with different data rates, the communication is possible. Okay, uh, compared to circuit switching, where the both ends, the transmitter and the receiver, has to maintain the same data rate. Okay, so packet switching had that advantage, and that concept of having different data rates is possible because of this flow control. Okay, so flow control basically takes care of the fact that not all machines have the same speed, and therefore you need to regulate the process of sending data between a fast sender and a slow receiver. Okay, and this particular thing is taken care of by this flow control uh, part of the protocol. And then finally you have error control. So you need to detect the errors and recover them so that you can ensure an error-free transmission. Okay, so moving on with the protocol. So there are certain key features of a protocol. The first one is syntax. This is concerned with the format of the data blocks. Then comes semantics. So this includes control information for coordination and error handling. and then comes the timing, which includes the speed matching and sequencing. And the different agents involved in the communication are these three applications that exchange data between computers. So one example of an application is email. So your email is an application, your web browser is an application, and then you have several applications which you uh, shortly call apps that you have in your phones. So these are the applications. Then the computers that are connected to the networks, and the computers hosts the applications, okay. And then comes the networks that transfers data from one computer to another, okay. So these are the different agents involved in the communication. So now talking about protocols. So these protocols, which are a set of rules, they are actually defined into these layers, okay. So so every communication network can be divided into certain layers, okay, and each layer has its own set of definite rules to follow, okay. So in other words, each layer follows a definite protocol, okay. So why these layers are done, or why the communication networks are divided into layers, I will come to that shortly. But the first layering the like system is called TCP/IP layers, okay. We will also see there is another system of layers called OSI, okay. So TCP/IP layers divides the communication network into these 5 layers, okay. Physical layer, network access layer, internet layer, host to host or transport layer, and application layer, okay. So coming to the point that why this layering is done, let's consider the example of air travel, okay. So here the problem is your actual travel, the air travel, and the entire air travel is decomposed into a series of steps. Like you arrive at the airport, okay, you check in, and then you do boarding, and then your flight takes off, you travel through the air, and then you have at the departure airport you have the landing, then you come out of the plane, you deplane, you do baggage claim, and then you come out of the airport, okay. So you are entering the arrival airport, you are going through all these steps, and finally again at the departure airport you go through all these steps, and then you go out of the airport. So so imagine that these are the different layers, okay. If your entire air travel thing is separated into different layers, where your arrival is one layer, okay. So let's say this is the departing airport side, and this is the arriving airport. So in the departing airport, you arrive at the airport, you check in. So this is again a separate layer, check in, where all the different employees of the airline that take care of check in will be here and help you. Then in the boarding area, where when you reach the gates and when you do the boarding, there will be a separate set of employees employed by the airline to help you with the boarding, to scan your boarding pass and stuff. And then when you take off, the cabin crew, which is again another set of employees of the airline, they help you to make your travel comfortable. You are going through the air, you travel, your airplane is getting routed, okay, from one place to another in the air, okay. And then finally you land, and then you deplane, you do baggage claim, and then departure. So you can see that every layer has its own set of definite rules, and they are independent of each other. The check-in people are doing some different set of rules than the boarding employees and so on. So similarly, in a communication network also, each layer has its own set of functions. So when you are sending a message from a source to a destination, in the source side you are going through all these layers right from the application layer. So you as an user, let's say you are sending some data, so you are using an application, let's say email application, okay, and you are sending an email. The email message is then going through the transport layer, and the transport layer header is added. Then it goes to the internet layer, so another network layer header is added. Then it goes to the network access layer, so another header is added. And then finally the physical layer transports all these physical bits, ones and zeros, etc., and then they are received by the physical layer of the destination, and then all these headers are, read and stripped off in the receiver side. So um, and then you obtain the final message as it was sent, okay. And at each layer, when you keep on adding the headers, the message is known by a different name. So in the transport layer it's called a segment, in the internet layer it's called a datagram, in the network access layer it's called a frame, and so on. So you can see that why you are dividing the communication network into different layers, and each layer performs its task that helps you in the eventual transmission of the message from source to destination, just like the airline system, okay. So you have arrival, check-in, boarding, takeoff, then landing, deplane, baggage claim, departure. Similarly, you have application layer, transport layer, internet layer, network access, and physical layer in the source side, and then in the destination side you also have those layers that do the reverse operation. And finally you get back your message, okay. So so now let's focus on the details function of these layers. So physical layer, as I said, it covers the physical interface between the data transmission device and the transmission medium. So it takes care of all these transmission related activities, like what will be the data rate, what will be the modulation format, what will be the nature of the signals, etc., and other related matters. Then the network access layer is concerned with the exchange of data between an end system and the network to which it is attached. So the software that is used to perform the tasks of this layer is depends on the type of the network. So um, it can be X25 for packet switching, it can be Ethernet for LANs, etc. Then the internet layer, it uses the internet protocol called IP. So you must have heard about this term as an user of the internet. This provides routing functions to allow data to traverse multiple interconnected networks. And this TCP IP layer is implemented both in the end systems and also in the routers. And then comes the transport layer. It's also called host to host layer. So this commonly uses the transmission control protocol called TCP. From this actually the name TCP IP comes, okay. So this provides reliability during the data exchange, okay. So this provides completeness and order of the data, okay. And then finally the application layer, which is the user layer. So this supports the user applications, um, and it uses separate modules that are typical to each different type of application. So for example, your email uses SMTP protocol or simple mail transfer protocol. For file transfer, you use FTP protocol, and then for web browsing, you use the hypertext transfer protocol or HTTP. So this diagram actually gives you an overview of the entire TCP/IP concept. So you see that this is your, let's say this is the source and this is the destination. So these are the two machines, host A and host B. And then you have several apps running on host A, okay, that are connected to the TCP layer through these ports, okay. So TCP layer has different ports or service access points. So these apps are talking to the TCP layer through these ports, okay. And these ports, they form a logical connection, a logical TCP connection between these two hosts. So this is not a actual physical connection. The actual physical connection goes through all the layers, then through the networks all the way to here, okay. But the logical connection between the TCP ports of the two end systems, host A and host B, is this one, denoted by this dotted line. Okay, then the TCP layer is there to do its function. Then comes the IP layer, okay, and IP layer has some IP addresses. So all the devices that are attached to the network has some IP address, and IP layer takes care of those addresses and finds out like where your packet has to be sent. Then the network access layer and the physical network and the physical layer, and then you can see that your messages passes through several networks. So it goes through a network one, then there is a router that sits in the interface of these two networks, and then it passes the message to network 2, and then it reaches the final host. Inside your networks, like this network 1 and network 2, inside these networks also you will have like several switches connected like this, which are not shown here, okay. So like this, okay. So there will be a router here on each of these nodes, okay, which will pass your messages, okay. So this is the zoomed schematic diagram of a router. So a router only has the IP layer and the network access protocol layer and the physical layer, okay. It doesn't have the higher layers, okay. It doesn't have a TCP layer, it doesn't have an application layer. So the function of the router is just to forward the packet. So all it needs is to check the IP addresses and find out what will be its next destination, and then it goes through the network access protocol, and then there is a physical layer to the router as well, okay. So so now there is also an alternative representation which is called OSI model or OSI layer, okay. So you had TCP IP uh, which had 5 layers, and this OSI is an alternative approach where you have so TCP IP have 5 layers, but this OSI approach has 7 layers. So there are some similarities between these two. So application layer is here, which was also there in TCP IP. The physical layer was there, the transport layer was there, and then you can see that there are some extra layers here, presentation and session layer, okay. So let's see what are these. So application layer is more or less the same in OSI and TCP IP. So they provide access to the OSI environment for the users. So users are directly connected to the application layer, both in TCP IP and also in the OSI. Then the presentation layer, which is the new layer that is introduced in the OSI model. This provides independence to the application processes from differences in data representation. Okay. Then comes the session layer, which is another new layer. So this provides the control structure for communication between applications. And it also establishes, manages, and terminates connections between cooperating applications. Okay, so I will encourage you to go through the details of these layers again in the William Stallings' book that I had referred as textbooks. Okay, um, I would encourage you to go through the details which are nicely written in the book. Then the transport layer. Okay, so transport layer was also there in the TCP/IP. Here also we have that, and the functions are same again. So it provides reliable, transparent data transfer between the endpoints, and also it provides end-to-end error recovery and flow control. Then comes the network layer. So this provides the upper layers with independence from the data transmission and switching technologies used to connect systems. This is responsible also for establishing, maintaining, and terminating connections. Then comes the data link layer, which provides for the reliable transfer of information across the physical link. Um, so I'm just going through these slides. There is nothing much to explain. I will encourage you again to read the book for this part of the lectures. Okay, so these are just uh, information on how these layers function. Okay, and then finally the physical layer. So this is again as similar to the TCP/IP scenario. This is concerned with the physical transmission of the bits over the physical medium, and it deals with accessing the physical medium as well. Okay. So this is a comparison of the two approaches, okay, or the two architectures. So this is the OSI with its 7 layers, and this is the TCP/IP with its 5 layers. So you can see that most of the functions of the application, presentation, and the session layer in the OSI is taken care of by just the application layer in the TCP/IP. Then some part of the session layer and the transport layer is taken care of by the transport layer in the TCP/IP. The network and data link layer together in your OSI can be functionally similar to the internet and the network access layer of the TCP/IP. And the physical layers are the same in both the cases. Um, so now both these systems or both these architectures are there, but the TCP/IP architecture dominates because the TCP/IP protocols matured quicker than similar OSI protocol. Okay, so so when the need for interoperability across networks was recognized, only TCP/IP was available and ready to go. So OSI layer system came very late, and by that time TCP/IP was very mature, and nobody wanted to mess with the TCP/IP scenario. And also the new OSI model is unnecessarily complex. So what it accomplishes in 7 layers can be done with fewer layers in TCP/IP. So again, let's say if I ask you, you all as students will also probably prefer TCP/IP because you have to remember less number of layers and less functionalities from the point of view of your exams, let's say. So this is something where you know TCP/IP is always a winner. So let's move on with the internetworking terms. So we have a communication network. So this lecture is all about communication network. Okay, so we are studying everything under the broad category of communication networks. So communication network is a facility that provides a data transfer service among devices attached to the network. Then the internet is basically a collection of communication networks. So there can be many communication networks, each of them interconnected by bridges or routers. So this is also shown here in this diagram here. So you see there is one network here, there is another network here, and they are connected by a intermediate router. Okay, so this is what is meant here when we say that the internet is a collection of communication networks interconnected by bridges or routers. Then intranet is an internet used by an organization for internal purposes. So intranet is something which your college or university just uses for its internal purposes. Okay, it's different from the internet. Okay, then the end system, we saw what is an end system is. So this is a device which is used to support end user applications or services. So this is your phone or tablet or PC, etc. Okay, then the intermediate system, this is a device used to connect two networks. A bridge is an intermediate system used to connect two LANs that use similar LAN protocols. And a router is a special case of an intermediate system used to connect two networks that may or may not be similar. Okay, so the functions of a router are these. So they provide link between networks. They also provide for the routing and delivery of the data between processes and end systems. They also provide these functions in such a way as to not require modifications of the networking architecture of any of the attached subnetworks. So to do that, the network differences that the router must accommodate are these. So it should have different addressing schemes for assigning addresses. It should also accommodate different maximum packet sizes that require segmentation. Then it should have differing hardware and software interfaces, and it should also facilitate the provision of unreliable services. Okay, so these are the functions of a router. So again, I would again encourage you to read the book that I referred by William Stallings, where you will get more details than what is written here in this slide. So with that, I stop here for this lecture. I will see you in the next video lecture. Thank you.